I'll frame this in terms of climate. The UN panel on climate change, this is the IPCC, released its 4th assessment report in 2007. For climate, the IPCC makes subjective estimates of the temperature sensitivity. That's the response to a doubling of carbon dioxide. And they give two different numbers. One is that there's a 2/3 chance that the sensitivity is between 2 and 4.5 degrees. And then there's another one which is single-sided, which is that there's a 9/10 chance that it's above 1.5 degrees. Now, for oil, gas, and coal production, the IPCC works with scenarios. And the range in these scenarios is supposed to be meaningful. There's a statement that they reflect the current range of uncertainty. This is the oil production in the scenarios. And what you can see is that there's a large range. It's 5 to 1 over this 100-year period that they're showing. But there's more to this. If you look in the, I'll try it on this side. I think that's a little bit more the balance. You can see in some scenarios we're pretty much out by 2100, while in others we're still growing in 2100. And so there's an implied range, including the years after 2100, which is larger, maybe 10 to 1, very large. Now, the goal of the talk is to reduce these uncertainties, replace the subjective estimates and the scenarios with standard, simple, not high level, but simple statistics. And we're going to start with U.S. oil, and then look at British coal, and then we'll spread out to world coal, world oil and gas, and then we'll see what implications there are for climate. Now, the main work in this is the coal work. Everything else follows from that. There's not much outside of the coal that would be considered new, and so the coal is really the core, and then the other aspects are the results, the implications of that. And so there is a paper on this which has just been published, and I can send people a reprint if they send me an email. I can return it. Now, the emphasis is on reducing uncertainty. Now, it's not a statistics talk, but we'll use some of the language from statistics. We start with data, which might be a production series, might be temperature measurements, and then we'll have a model for it. And these will be simple models. There'll be some that look like S curves, and then others that are straight lines. And now the residuals are the difference between the data and the models, and we'll be picking the best model. That's a little bit of a complicated idea, but I'll explore it later for you. And then we'll use that to make projections. Now, the word uncertainty to a statistician in this context means we've made a group of projections, and it's the spread in the projections that we're talking about. One example, it's a simple one, which is a range. You take the biggest number and the smallest number, that's your range. Civil engineers, for example, a one-sided version of this, they might design for the biggest flood that they've had in 100 years. Now, in some special circumstances, the residuals have a simple enough structure that you can do better with this. You can calculate what are called replications, and these are effectively alternative histories. They have the same statistical properties as the real history, but they would differ. And you can then use these replications to calculate what the statisticians call a confidence interval. And this is a statement, say, a 90% confidence interval of 1 to 2 degrees, and that means that there's a 90% chance that we're in that. That includes the correct answer. Now, a warning, confidence intervals are absolutely standard in statistics. My wish is that people use some language that wasn't quite so positive about it. I like uncertainty index. And the reason is that inevitably, it's a number that's useful, but there are real limitations. They depend on the form of the model. You change the model, a different kind of model, you get a different number. Inevitably, there are uncertainties, maybe major ones, that are left out. And often, particularly, well, when you talk about projections, the models can break down. Something can change that we haven't taken into account. And we'll see examples of this in the past. King Hubbert was a geophysicist at the Shell Lab in Houston, Texas. In 1956, he wrote a paper suggesting the possibility of a peak in U.S. oil production in 1970. Now, this is what happened. It actually did peak in 1970. And as you can see, it's been pretty much downhill since then. This is a different way to plot the same data. It's a cumulative plot, which means we add up the production as we go along. Now, you can see it's changed our bell-shaped curve into an S curve. and it's also smoothed it out. You don't see that second peak for Alaska anymore. Now, on the right, you can see a gray curve. That's a cumulative normal from statistics, and the shape of that's actually fixed, but I've scaled it to fit the data, and you can see it's a good fit. And for that reason, we can use the top of the scale, that's this number here, 227 billion barrels, as an estimate, a projection for the long-term production. And by long-term production, I mean total production. That would be past production, future production, the whole thing. Now, this is one page on how I do the calculations. It is an approach where we linearize the data. There's a function that will linearize a cumulative normal. It goes with the name propet here. And then there's another S-curve we'll use called the logistic function, and then there's a transform for that called the logit function. Now, and you can see this has turned this cumulative data into something very close to a straight line, and then I'll pick the long-term production that gives the closest plot to a straight line. And the number I use for what's the closest thing to a straight line is this number called R squared from statistics, and that is a number that's easy to calculate. It takes about, just try a range in Excel, and it takes about 1 second for Excel to find the thing. So you could do thousands of these if you choose, if it works into your statistics. Now, here are the residuals, and it will give you a sense of how these plots look. I always express these in terms of time. And so I think of this S-curve as a kind of production schedule. And if we get ahead of the production schedule, then the residuals will be positive, some number of months or years. And if we lag behind, then the residuals will be negative. Now, the thing that's interesting about these is that for us, 1901 was our first big gusher. This was Spindletop in East Texas. And since 1902, the residuals have been 10 months or less over that whole 100-year period. And they're currently 4 months, so we're within that range. Now, the fit's a good one, and it raises the question, could we have done this fit earlier? Could Hubbert have done it in 1956? And what we're interested in here is the blue curve. These are historical fits, and by that I mean I only use the data that was available in that year. So there's a number at 1946 there. That's something that the calculation someone could have done in 1946. Now, these have a very similar structure when you look at production curves for different regions and different fossil fuels. The early years are unstable. You're in the early part of that S-curve, and you can't nail it down. And usually they go off the top of the graph, and that's what they do here. But here, around 1946, they've settled down. And since then, it's been within a 14% range. And so that would be my estimating range for U.S. production. Now, you also see circles. It turns out in Hubbert's day, there were many people that wanted to estimate long-term production. And so these are the numbers for them. And now you see big circles here. Those come from people who work for the government. And then there are small circles. Those come from people who work outside the government, maybe a foundation, maybe a private company. And the interesting thing is the current estimate we have is exactly consistent with the median for the non-government estimates. But the government estimate's much bigger. It's about twice as big. And the current estimate, which comes from the Geological Survey, is right in line with the earlier estimate. So it's high. Now, it raises the question, what's going on with the government estimates? Now, we'll be exploring different aspects of this. So I'm just going to start with a quote from Ken DeFaze, who's a popular writer in the U.S. on fossil fuel supplies. And he says there is a tendency for government estimates resource estimates to be high. And it's that when people do resource estimates, they have to make a lot of choices about criteria to use. And he says people in government tend to choose the bigger numbers. And we'll test this idea in a simple way as we go forward. And I'm going to call this DeFaze's law of bureaucratic resource estimates. Now, we'll switch to British coal. Now, Britain was the largest producer of coal in the 1800s, and it's produced a lot of coal. In energy terms, it's the cumulative equivalent of Saudi oil. Britain has its Hubbert. His name was Stanley Jevons, and he wrote a book in 1865 called The Coal Question. He was interested in how long British coal would last. People had done a static calculation where they expressed the reserves in terms of the current production, and when you did that, you came up with about 800 years. But Jevons had noted that production had been growing at 3.5% per year, and so he's got a plot for this in his book that shows it rising, and he argued that this would shred this calculation, and this curve crashes sometime in the 20th century. You run out. Now, here's what happened. British coal production peaked in 1913, and you can see it's been pretty much downhill since then. There are a couple of ways that you can give perspective on this. The last time British coal production was this low, Napoleon was alive, so it's almost 200 years back in time. Another way is, at the time, Britain was the Australia of its day. It exported 30% of its production. Now it burns more Russian coal than British coal. Now, we can do the same kind of curve fits we did for U.S. oil. And they look, it's a similar pattern, unstable in the early years. Around 1900, it's stabilized. It's been in an 11% range since then. Now, we're further along than for U.S. crude oil, and this, to me, looks pretty good. I think this 11% range will capture the actual value. Now, here's another comparison we can make. Because of Jevons's book, there was a Royal Commission on Coal Supplies that made a supply estimate, and they came up with that number that's plotted there. And you can see when you look at the following numbers here, that set the standard for British reserves until about the late 1960s. Now, since 1871, we've had 140 years, and we can test the Commission on their work. It turns out that the UK has produced only 18% of the coal that was thought to be mineable at that time. And it's also clear now, at least what one of the problems is that the criteria they chose were too optimistic. They chose 1-foot seams down to a depth of 4,000 feet. Jevons used the number from Edward Hall here, and Hall had criticized this choice of 1 foot at the time, that it was too optimistic. Now, there's another thing you can see in the curve, is there's a collapse of these reserves in the late 1960s. Now, the way I interpret this is reserves are supposed to have an economic component to them. And at some point, there's a realization in the government that there are not good prospects for new mines. And at that point, the accounting basis for the reserve shifts from all the coal in the country to the coal that you can get at mines that are producing or mines that are planned. It's a much smaller number. Now, I think it's clear that judgment was correct. We now have 5 collieries left that have producing longwall faces. There were 800 in 1972, so it's really a collapse. And each of these 5 were producing by 1968, so there's no new one since then. Now we'll shift to American coal. This is actually a modern picture, and I'll take a little break from the graphs to talk about what these men are doing. These are the 2 traditional manual jobs in an underground coal mine. The cutter here on the left typically cuts a slot near the bottom of the seam as much as he can reach with his pick. And then another person will go and drill holes, put in explosives near the top of the seam, and then knock it down, and then it's loaded. Very tough way to make, you never get to stand up as far as I can tell. It's tough living. Now, this is Pennsylvania anthracite. That picture came from an anthracite mine in Pennsylvania. And this shows a similar pattern to British coal. Peaked in 1917, and we're way down now since then. Here are the same curves that we showed for British coal. These are the historical long-term fits. It's the blue curve. Similar structure. Starts to stabilize around 1900. It's not, the range is wider than for British coal. It's not quite as well behaved, but it looks like it's in the right range to capture the long-term production. But then we also have the reserves, and this gives you the same kind of picture that we had for British coal, that they seem to be too high. The other discouraging thing is each time you do a new survey, you get further off from the eventual result. And then there's a collapse at the end, just as for British coal.